Okay, I want to describe some research I have been doing with Irina Bohemsky and Kara Rood. My contribution to this research is to develop a smartphone app that can screen for preeclampsia. So this talk is in two parts. Part one is more or less descriptive. I'm just going to describe a test called the Congorate dot test and the app that we use along with that test to screen for preeclampsia. And part two is a little bit more technical. I want to explain some of the science behind the test and especially explain why the tests and the app work. By the way, if this presentation appears blurry on your screen, then please change the resolution at which you're watching. And you can do that by clicking on that little gear wheel symbol there. And in the drop down menu for resolution, picking a resolution that's 480p or higher. There's one more thing I want to say before I launch into the main part of my talk, and that is that this app would be impossible without some remarkable discoveries that Irina Bohemsky made. These are now in print. They just appeared in Science Translational Medicine, and if you're interested in the scientific details, I urge you to download that paper and read it. Let me start by saying something about preeclampsia. Preeclampsia is a disease or a disorder that occurs in pregnancy, and women who are preeclamptic develop high blood pressure and have excess protein in their urine. Its incidence is, at least I think it's surprisingly high. It's about 5 to 6%. So approximately 1 in 20 pregnant women become preeclamptic. If preeclampsia is not diagnosed and medically treated, it can lead to convulsions, coma, and eventually to death. Now, preeclampsia is not a big problem in developed countries. Most pregnant women in developed countries go to see a physician, and if they are preeclamptic, they are diagnosed pretty quickly and their preeclampsia is managed during the pregnancy. The problem is in underdeveloped and developing countries where pregnant women don't have access to physicians. The WHO estimates that about 63,000 women die every year from preeclampsia. And the reason for that is pretty clear. These women live in such impoverished conditions that they don't have access to healthcare professionals who can take their blood pressure. They don't have access to labs that can measure the protein in their urine. And that really is our motivation for developing this app. The app is used along with a test called the Congorate dot test. Let me just show you what the Congorate dot test is and what the app does. So this is the Congorate dot test. It's quite simple. You start by collecting urine from the pregnant woman and you mix with the urine two dyes, a dye called Congo red, which is of course red colored, and a dye called erioglycine, which is blue. Both of these dyes are quite inexpensive. In fact, erioglycine is commonly available as a food dye. It's called blue food dye number 1 in the US. So once you mix urine with both of these dyes, you take a drop of that mixture and you put it on paper. After experimenting with a number of papers, we found that the kind of paper that's used to print mailing labels works really well with this test. So that's the paper we use. When you put a drop of the mixture on the paper, the drop gets absorbed into the paper over its initial area of contact. And once the drop is absorbed, it then spreads out into a larger circle. So let's see what happens if the urine in the drop is normal. If the urine is normal, then all of the Congo red dye binds to the paper immediately over the initial area of contact, while erioglycine, the blue food dye, spreads out with the rest of the urine, and you get this really nice separation of red and blue. If the urine comes from a preeclamptic woman, then the Congo red dye also spreads out along with the urine. It does not bind over the initial area of contact, and you get this nice overlap of the red and blue regions. So that really tells us whether the urine is normal or preeclamptic. Okay, here are some real life samples. So this is the test done on urine from a normally pregnant woman. Here is the test done from urine from a severely preeclamptic woman. And you can see that for the normal urine, there's a clear separation of the red and blue dots. And for severely preeclamptic woman, the red and blue regions overlap. And by the way, there are these intermediate cases also where the overlap of the blue and red regions is in between the normal and severe preeclamptic cases. It's because we have these intermediate cases that we eventually decided to do some quantification of this test, and I'll talk about that when I come to the app. So this test we call the Congo Red Dot test, and there's a couple of things you should know about this. The dyes that are used in this test are extremely inexpensive. The patent on Congo Red expired many decades ago, and as I said, Erioglycin is just a blue food dye. And all you really need to do this test are the two dyes and paper. So the material cost of this test is less than 4 cents. And we now in fact have a kit that you can use to do the Congo Red Dot test. So let me just show you the kit and how it's used. So that's what the kit looks like. It's a piece of paper that's printed on a computer printer. It has a plastic dropper in it. The dropper has the dyes pre-mixed and one end of the dropper is sealed. You can break off the seal and then take a urine sample and draw that sample up into the barrel of the dropper. As you draw the sample up, it mixes with the dyes in the barrel, and you can mix that a little bit more thoroughly. Then all you have to do is put one drop of the mixture on each of the white squares of the paper, and you'll soon see that the paper absorbs the drop and it spreads out. While the drop is wet, everything appears blue, and when the drop dries, the red of the Congo Red becomes a little bit more apparent. So that's the kit, and that's a test being performed using the kit. So once you have the Congo Red Dot test, we can try to make the screening of preeclampsia a little bit more quantitative by coming up with an objective measure of how much the Congo Red dot and the blue dot overlap. And that's what our app does. Basically, it takes an image of that dot and from it creates an area that contains the entire spread of the urine and an area that contains spread of just the Congo Red dot. And then we calculate the ratio of those two areas. So the ratio of the red area to the entire area of the urine, and we call it the Congo Red area ratio. Now keep in mind, if the urine comes from a normally pregnant woman, we expect this ratio to be small because we expect the red dot to be much smaller than the entire urine dot. If the Congo Red Dot test came from a severely preeclamptic woman, we would expect this ratio to be close to 1. So high ratios mean very likely that you are preeclamptic. Low ratios mean very likely that you are normal. So the app sounds fairly straightforward, but in fact there were lots of challenges in developing this. Most of the challenges come from the fact that we expect the app to be used in the field, and there are lots of things you cannot control in the field. So in particular, you cannot control the type of illumination that's falling on the paper when you take an image of the Congo Red Dot test. And to show you that it matters, here's a case where the same Congo Red Dot is imaged in three different lighting conditions. So in diffuse daylight, in indoor incandescent light, and indoor fluorescent light. And you can see that the colors that are captured by the camera are actually quite different. They depend a lot on the kind of illumination that's being used. The other problem that comes up is that there is very often an illumination gradient across the image. So here's an example of what I mean. So in this case, the amount of light falling on the top of the Congo red dot is much less than the amount of light falling at the bottom of the Congo red dot. And so the app has to actually correct for this. Without correcting for this, it's likely to misinterpret what the region of the red dot and the region of the urine might be. And the last challenge we have is that we want to keep this app computationally really simple. So those were the real challenges that we had in developing the app. We now have an app that takes care of all of this. It takes care of variable illumination, illumination gradient, and is computationally quite simple. So with that app, we can now calculate the area ratios. So we did some preliminary testing to see how well the app works. And we collected urine from 40 pregnant women, 21 of which were normal and 19 were preeclamptic. We did the Congo red dot test with the urine, and then we took images of these Congo red dots under different lighting conditions and used the app to calculate the Congo red area ratio. This is what the ratio looks like. The x-axis shows the different samples. So there are 40 samples. The first 21 of them are normal, the next 19 are preeclamptic. And the y-axis shows the Congo red area ratio that the app calculates. So now notice that for the normals, the Congo red area ratio is quite small. They're all below zero point 0.2. For the severely preeclamptic, most of the ratios are quite high, they are near 1. There are a few cases where the ratios are less than 1, and this is really why we need the quantification. There are some cases in the preeclampsia category where the ratios are closer to that of the normals. And when we examine these cases, they all turned out to be cases of mild preeclampsia. And by the way, notice that these numbers are reasonably insensitive to the kind of illumination that's falling on the Congo red dot test. After doing some ROC analysis of this data, at a threshold of about zero point 0.2, we get 100% specificity and 85% sensitivity. And what that means is, at that threshold of zero point 0.2, we classify all normally pregnant women as normal, but we misclassify about 15% of preeclamptic women. And amongst those 15% that are misclassified, there are many cases of mild preeclampsia. And that really is all I wanted to convey in the first part of this talk. We have what seems to be a promising and an inexpensive tool that screens for preeclampsia. All you have to do is collect urine, mix it with 2 dyes, do the Congo red dot test, and take a picture of that test with the smartphone app. We do have plans to work on a large sample size to see whether our statistics will hold in a larger group. I want to acknowledge support from a USAID grant which made a lot of this research possible. And I have one more acknowledgement, which is to acknowledge my student, Angie Perez, who took the algorithm and developed an Android app for it. What you see here is the app as it is now deployed on a Google Nexus 7. That's the app as it appears on the Nexus 7, and that's the app being used to image a Congo red dot. And that is the end of part 1 of my talk. You can stop here if you like. I'm going to continue and explain to you why all of this works. Why does the Congo red dot test work, and how the app takes care of all of these problems we have with illumination. The science behind the Congo red dot test is based on this new discovery that Irina made. And this paper, which reports the discoveries, is really interesting. It has a lot of new findings in it. Two of those findings are important to explain the Congo red dot test. So let me just point out what those findings are. The first finding is that normal urine has no or very few misfolded proteins, whereas preeclamptic urine has many misfolded proteins. Now, it's important to understand that we already knew that preeclamptic urine has more proteins. That's not a new discovery. The new discovery is that not only does preeclamptic urine have more protein, some of those proteins are misfolded, whereas normal urine has no misfolded proteins at all. The second discovery is that these misfolded proteins are of a type that are congophilic, which means that Congo red, which is this red dye, binds to these misfolded proteins in solution. Now, Congo red has really interesting properties. So, as I said, it binds to these misfolded proteins, but it turns out Congo red also binds to cellulose, to paper. But there's a difference between the two cases. It turns out that Congo red's affinity for proteins is greater than its affinity for paper. And what that means is the following. If Congo red is already bound to misfolded proteins, then it will no longer bind to paper. On the other hand, if Congo red is not bound to proteins, then it will bind to paper. And it's this difference that gives us the Congo red dot test. Here's the explanation. Let's say we have normal urine that we have collected. Now, when you add Congo red to it, because normal urine has very few misfolded proteins, most of the Congo red in the solution is unbound. It's not bound to anything because it doesn't bind to normal proteins. When you put a drop of the solution on paper, as the solution gets absorbed into the paper over the initial area of contact, the unbound Congo red immediately binds to paper. And this binding takes over the contact region. And that's why you get this small red dot, whereas aeroglycine, which does not bind to anything, spreads with the urine and you get a larger blue dot. Now suppose that the urine is preeclamptic. In that case, Congo red now is already bound to the misfolded proteins in the preeclamptic urine, and when it's bound to the misfolded protein, it cannot bind to paper. So then as the drop diffuses out to a bigger circle, the misfolded protein also diffuse out, and the misfolded proteins carry with them the bound Congo red, and therefore you get a bigger dot for the Congo red than in the normal case. And that's really why the Congo red dot test works. So let me now explain how the app works and how it takes care of all of these vagaries of illumination. So the way the app works is we take a color picture and we independently process the blue channel and the red channel. And one of the first things we do is we compensate for variable illumination. And we do that by looking at the boundary of the image. So notice that the variable illumination can be measured by just looking at the illumination along the boundary. And so what we do is we do a form of linear regression to model which part of the boundary is brighter and which is darker, and then we subtract out the regression from the image, from the entire image, and that takes care of variable illumination. So that then gives us two images in which most of the variable illumination is gone. And then we do something called segmentation, which is an image processing technique that takes an image like that and produces an image which simply contains the foreground and the background separated out. So we segment the blue channel, we segment the red channel, we then combine the red and blue channel to give us the overall spread of the urine drop, and then we calculate the ratios to get the Congo red area ratio. So that's basically how the app works. And that brings me to the end. I just want to mention a couple of things. What you just heard is a slightly longer version of a talk that I gave at the IEEE Healthcare Innovation and Point of Care Technologies Conference in Seattle in 2014. There is a paper that describes the algorithm that we use in the app, and you may be able to download a copy of that paper from the IEEE website, or you can download that paper from my website.